Today we're going to start our final section, 12.2, where we compare the means. You can use a date of May 12th. So the learning objectives in this section, we're going to go through contrasts and we'll do some examples and we'll look at multiple comparisons and then we'll briefly touch on the power of the F-test. Don't panic, we're not doing any power calculations. At the end of the last section, we talked about running the ANOVA F-test to see if there was a difference between different group means. So again, we're asking the question, are there significant differences among the observed group means, and are they statistically significant? Usually when you set up your test, you already have some kind of preconceived ideas about which means might be different or which ones might be the same. So prior to running the test, the ANOVA F-test, we're going to set up some contrasts. So once we determine that the ANOVA F-test is significant, then we can further our examination and look at which treatments are different from which. So are group 1 and 2 the same, or is group 1 closer to group 5? Or is 3 and 4 significantly different? So we're going to look at that grouping and see how they compare. We said in a previous lesson that contrasts are planned comparisons. You do set these up before you start the experiment. We don't want to do the experiment and then start data mining. We don't want to look for things. We already have some kind of clear idea of what we think we will see. And if the ANOVA F-test is significant, then we'll go on with what we think is happening. All right, so basically a contrast is a linear combination, and we're going to set some linear models up in a few minutes. It's going to represent the population mean. This is the Greek letter psi, P-S-I. And to calculate this, we would take the sum of A sub I, which will represent some coefficients that you're going to assign, times their mean. When you set these coefficients up, they have to sum to 0. What we'll do is we will calculate a sample contrast, which will be our unbiased estimator for psi, because we technically won't know what psi is. So instead of using mu sub I, we'll actually use our x bar sub I for each individual observation. And each observation will have its own unique coefficient assigned to it. All right, so for this example, this is where we're going to learn how to assign our linear coefficient. It says patients are given either drug A, B, C, or D. D is actually the placebo. So in the first contrast, you think there might be some kind of significant difference between A and D. That tells me I'm not doing anything with drug B or drug C. So the coefficients there are actually 0. A and B, whatever coefficients you assign, have to add up to 0. So what I'm going to do is I'm going to make A positive 1 and D is negative 1. This is just me assigning values. You might assign A to be negative 1 and D to be positive 1. In either case, both of us would be right because those coefficients add up to 0. In the next example, it says the difference between the average of A and B. So we're lumping A and B together as one group, and then the average of C and D, they're being lumped together as their own group. So don't forget, these coefficients have to add up to 0. So if A and B are together, maybe they're both positive 1s, that would give us a positive 2, and then C and D, because they're a contrasting group, are both negative 1s to get negative 2, but the sum of all these pieces would be 0. In the third example, it says the difference between A and the average of B and C. The placebo is not being considered at all, and therefore it gets assigned a coefficient of 0. So A, you get to choose. Maybe A is 2, and B and C are both negative 1. So those coefficients would add up to 0. In the book, they like to use halves. So the book might assign A to be a positive 1, and B and C are -1/2. You can use the halves or the thirds or the fourths, but I think using whole number integers actually works a little bit better. For the last one, the difference between A, and it's the average of B, C, and D. So A is a standalone drug. I'm assigning it a coefficient of 3, and then B, C, and D are all -1s to get that sum of 0. But maybe you assign it a -3, and then B, C, and D have to be +1s to offset that sign. So hopefully that's clear on how to assign a coefficient. You get to set them up. Now, since we don't know the actual value of psi, and we'll be using our own contrast calculation, we also need the standard error for the contrast. So this is the formula to find the standard error, and subscript C is contrast. We're going to use a pooled standard deviation. And then what we'll do is underneath the square root radical, we're going to take the coefficient assigned to the first observation and square it. And then it's divided by that sample size. And then we would add to it the coefficient squared for the second observation over the second sample size until we get a grand total. When we set up our test, we are testing the hypothesis of the null, where psi is equal to 0. The test statistic associated with this is a t-statistic. The numerator C would be calculated using your coefficients and the x-bar values and the standard error that you just calculated from this formula above. And we'll go through degrees of freedom when we actually do an example. Your alternate hypothesis could be one-sided or two. If you're truly not sure, you can just say psi does not equal 0. Make sure, though, you multiply p by 2. We can also calculate a level C confidence interval for psi, and this is done in the classic way. So we would take our numerical value for our contrast C. We would calculate our T star. That should be a superscript, not a time sign. Remember, when you type it in to find the area, we have to ignore that bottom tail. And then you would also use your standard error for the contrast. So we can test the hypothesis to see if it's significant. We can also tell if our value might be contained in our confidence interval, just like we have had in the past. The book says it might be more effective to estimate the size of the effect using a confidence interval. So if your value is not contained in there, which is 0, then we know that we probably have significant evidence. This is really not any different from any other inference test that we've run before. All right, there's no homework associated with this set of notes. If you do have any questions, please feel free to contact me. Have a great day.